Friends, welcome to video lecture on dynamics of machinery. In the today's lecture, we'll discuss about numericals on free damped single degree of freedom vibration system, session 5. So let us start first problem. The vibrating system consists of weight 10 Newton, spring of stiffness 10 Newton per centimeter and a damper of damping coefficient 0.05 Newton second per centimeter. Find the damping ratio, second point logarithmic decrement, third point damp natural frequency. So in this case, see what is the given data. Here the weight is given 10 Newton. So we know the relation between the weight and mass, W equals to mg. So from that we can get the value for the mass, like this one 10 by this one 9.81. So we can get the value for this one as 1.204 kilogram. Okay, so get the value for this one in terms of kilogram. Okay, in short. Next one, the spring stiffness is given. So K equals to 10 Newton per centimeter with us. So convert this one also in Newton per meter, okay, by multiplying 10 raised to plus 2, okay, or in short you can get the value for this one as 1000 Newton per meter. Next one, the value for actual damping coefficient is given, that is 0.05 Newton second per centimeter, in this way given. So what's about the next one? Just convert this one also in meter by multiplying here 10 raised to plus 2, okay, because centimeter term is with us in denominator, okay. So we can get this one in Newton second per meter, like this. So what's about the value for this one? 5 Newton second per meter. What's about the value for omega n from this one? So omega n is nothing but square root of k by m. What's about the k? K already given 1000, okay. What's about the m? Mass with us here 1.024 kilogram. So after solving we can get the value for omega n equals to 31.3050 radian per second, okay. So once we get the value for this one, my target is to get the value for first point damping ratio, okay. So in that damping ratio where we can require this omega n, okay. Now see the relation for the damping factor or damping ratio. So first one, the meaning for damping ratio and damping factor is same, okay. Damping ratio, that is zeta equals to C divided by Cc. This relation we know, okay. So what's about the Cc? Already we found the relation for this one C, like this one 2 into m into omega n. So here we can require the natural frequency. So what's about the Cc? The value for the Cc we can get in this way after putting the value of mass and frequency term. So here 31.3050, okay, this is the value for omega n with us. So after solving you can get the value for this Cc as 63.8872 Newton second per meter, like this one. So what's about the this term zeta? Therefore zeta is nothing but C divided by Cc. So C term already given in the problem, actual damping coefficient. So here zeta is nothing but it is the ratio of actual damping coefficient to the critical damping coefficient. Critical damping coefficient already the calculations done by us for that. Cc equals to 2m into omega n, okay. So from this one we can get the value for Cc. So once again just see this zeta term, it is the ratio of C divided by Cc. So C already with us 5, Cc already calculated by us 63.8875. So after calculations, you can get the value for zeta as 0.07826. Okay, this is the answer for first point. Now, next point with us, our next target is to get the value for delta. Okay, that is the logarithmic decrement. So logarithmic decrement, we know the straightforward relation between the logarithmic decrement and the damping ratio, that is zeta, or damping factor zeta. We know that relation. Okay, so logarithmic decrement delta is nothing but 2 pi into zeta divided by square root of 1 minus zeta square. In this way relation with us. Okay, already the value for the zeta with us, substitute here, so we can easily get the value for delta. 2 pi zeta 0.07826 divided by square root of 1 minus zeta square, means 1 minus 0.07826 bracket square, like this one. So after solving this, we can get the value for zeta, delta equals to, let's see the steps you are, if you are facing any problem, see the calculation part. Okay, here 2 multiplied by pi multiplied by 0.07826 divided by square root of 1 minus 0.07826 bracket square. Okay, to get the value for delta. So delta after calculation, you can get 0.493 in this way. Okay, so what's about the next part? Time natural frequency. Okay, this is the third part asked in the problem. So damp natural frequency, we know the relation, we know this relation between damp natural frequency and natural frequency of the given system. This is the relation with us, sort of 1 minus zeta square into omega n. In this way relation with us. Substitute the value for zeta here, zeta with us 0.07826 whole bracket square multiplied by omega n. Omega n, already calculations for the omega n with us 31.3050. In this way calculations for the omega n with us. After simplification, you can get the value for omega d equals to 31.21 radian per second. This is the answer for third point. If we compare this value with the natural frequency obtained, okay, so natural frequency, this is the natural frequency omega n with us. If you compare this with this one, ultimately the value for omega t found is less than this value. Okay, why? Because this is the damped natural frequency. Okay, here we can get the difference. In case of natural frequency, if you just see the reduction occurs here in the natural frequency, okay, because of some losses takes place in the system. Okay, so the frequency is here decreased. So we can get the natural frequency corresponding to damped vibrations are nothing but omega d equals to 31.21 radian per second. Now the next problem, an underdamped shock absorber is to be designed for a motorcycle of mass 200 kg such that during a road bump the damp period of vibration is limited to 2 seconds and the amplitude of vibration should reduced to 1/16 in one cycle. Find spring stiffness. Second point, damping coefficient of shock absorber. Okay, so first of all, say what is the given data. Here the mass is given, the mass value m with us 200 kilogram. So next one, the damped period of vibration is limited to 2 seconds. Damped period of vibration, time period is given 2 seconds. Okay, so from this time period we can get the frequency. Damped period is given, means here the damped period of oscillation. Okay, so you can get the value for damped natural frequency from this one. Okay, we know the relation between the frequency and time period. Okay, straightforward, it is the reciprocal of time period. Okay, so here the 2 pi divided by 2 second with us. After solving, we get the value for this one, omega d equals to 3.142 radian per second. Okay, next information is given, the amplitude of vibration should reduce to 1/16 in one cycle. Okay, if I assume x naught is initial amplitude and x1 is nothing but the final amplitude. Okay, so the relation between this one initial and final with us, so single cycle is given, only single cycle with us. So what we get relation here, x1 is nothing but 1/16 of 1/16 in one cycle. Okay, this is the information given. Okay, means we can get the relation between both this term like this one. So what's about the logarithmic decrement delta? So delta, we know the relation. I'll just write here logarithmic decrement. Yeah, decrement delta is nothing but 1 upon n log to the base e x naught divided by xn. Okay, so here delta is nothing but 1 upon n, only single cycle with us, so 1 upon 1 will come here, log to the base e x naught by this one xn. Okay, so x naught by xn, this ratio we can get directly here. Therefore here x naught by xn means here x naught divided by, if I take this x1 term here and 16 term here, we can get this relation like this one. So x naught by x1 is nothing but here 16. So 1 upon 1 log to the base e, here we get the 16. If you take the log of this one, okay, by considering this as e, so what we get here, and get the value for delta as 2.7725 in this pack. My target is to get the value for stiffness and damping coefficient of shock absorber. Okay, so to get that damping coefficient, it is very important to get first of all value for zeta. So initially the value for this one delta with us, from this relation easily we can get the value for zeta. Okay, so zeta is nothing but delta upon 1 upon 4 pi square plus delta square. In this way the relation with us, already we have seen this relation during the discussion of significance of logarithmic decrement. Okay, so just substitute here the value for delta and simplify this to get the value for zeta. So the value for zeta after calculations we get 0.4004. Okay, in this way. So once we get this value as the value for this one omega d with us, from this omega d our first target is to get the value for omega n. So after getting this value, just move towards the next part and just erase some portion from here. So we know omega d equals to square root of 1 minus zeta square into omega n. Omega d, already the value for omega d with us 3.142. Okay, this is the value with us. So from this relation, zeta is also with us 0.404 bracket square, sorry, this term square minus omega n. If you simplify this, you can get the value for omega n as 3.434 radian per second. So once we get this value, our first aim is to get the value for spring stiffness. So we know the relation, we know omega n equals to square root of k by m. This is the relation with us. So from this relation, our target is to get the value for k. Omega n already calculated by us here. Just substitute the value for omega n here. So 3.434 equals to square root of k by m. Mass is given 200 kilogram. Okay, simplify this and get the value for k. So k after calculations, the k with us 2358.283 Newton per meter. In this way, you can get the value for k. Next one, our target is to get the value for damping coefficient of shock absorber. For that, the value for zeta with us. Now see the relation between the zeta and that damping coefficient. Okay, so for that, the value of k with us, then value of m with us. Here the mass term is also with us. Mass already written. Okay, this one mass term with us. So we know the damping coefficient, that is C. Damping coefficient C is nothing but 2 into zeta into square root of km. This is the relation with us. Okay, so substitute the value of zeta. Zeta with us, zeta already calculation for the zeta done by us 0.404 multiplied by k with us 2358.283 multiplied by mass with us 200. Okay, so in this way we can get the value for damping coefficient. 554.518 Newton second per meter. Now see the extended discussion regarding this one. See, okay, we are facing the problem how this relation, okay, occurs. For that, we know zeta is nothing but it is the ratio of actual damping coefficient to the critical damping coefficient. Okay, if I take this Cc here, we know for this Cc, this is the relation with us 2 into m into omega n. So for this omega n, if I substitute square root of k by m, okay, so again if I for this one m, if I write like this one, zeta into 2 multiplied by square root m and square root m. Okay, the meaning for this one, the product of this one is automatically comes m. Okay, multiplied by this one square root of k by m. So 1 m get cancelled, 1 square root of m get cancelled, and we can get this relation k multiplied by m. So in this way I can write the relation for C. So next problem, the disc of torsional pendulum has a moment of inertia of 600 kilogram centimeter square, is immersed in a viscous fluid. The brass shaft attached to it is of 10 centimeter diameter and 40 centimeter long. When the pendulum is vibrating the observed amplitudes on the same side of the rest position for successive cycles are 9 degree, 6 degree and 4 degree. Determine logarithmic decrement. Second point, damping torque at unit velocity. Third point, the periodic time of vibration. Assume for the brass shaft G equals to 4.4 into 10 raised to 10 Newton per meter square. At what would be the frequency if the disc is removed from viscous fluid? Okay, so our first target is to get the logarithmic decrement. Logarithmic decrement, we know formula for the same. Delta equals to 1 upon n log to the base e x naught by xn. Okay, now if you look towards this one, the values for the successive cycles here given 9 degree, 6 degree, 4 degree. Okay, so successive amplitude, if I take the amplitude, this one first one as 9 degree, next one as 6 degree, next one as 4 degree. Okay, you can take the relation between the successive amplitude. Okay, like this one, successive amplitude. For that, if I say the successive amplitude means a single amplitude, if I consider it here, then we can get for the single amplitude n we get as 1, so log to the base e. If I consider the successive amplitude, then 9 by 6 will, okay, relation come, or same we can get the result by using this one. If I take the 6 degree by 4 degree, okay, so simplify this one and get the answer for delta. Okay, so if you look towards here, 9 by 9 by 6, so we get the value for a delta 0.405. This is the answer for the first point. If I use the second option, that is 6 by 4, 6 by 4, if you look towards the answer, we found the same result, 0.045. Okay, now next one, next target is to get the value for damping torque at unit velocity. So in this case, damping torque, so damping torque is nothing but here our aim is to find out the value for actual damping coefficient, that is C. So we know the, first of all we'll see the relation between this one C and zeta. Okay, so already we have seen zeta is nothing but C divided by CC. Okay, so what's about this C? C you can get this way, zeta divided by CC, oh sorry, zeta multiplied by CC. So I can get the zeta, already the value for the delta with us. Okay, so I can get the zeta, so zeta is nothing but delta divided by square root of 4 pi square plus delta square. So in this way I can get the relation for this zeta. So I can get the value for next one, CC. For that we know the relation. Okay, CC, how can get the value for CC? In previous problem already I have seen K into M, but in this case the torsional stiffness you have to consider it. Okay, so what's about that torsional stiffness? The value for I is given here, mass moment of inertia is given, means you have to modify this relation like this one, KT into this one I. Okay, so once you get the value for CC, okay, before that you need the value for this one KT. How can you get the value for KT? Now in the problem the value for the G is given, means KT can be calculated with the help of this relation GIP, okay, divided by L. Why this one IP is considered? Because the diameter and the length is given in the problem. Diameter for that rod is given, brass shaft attached to it of 10 centimeter diameter and 40 centimeter long. This information is given. So what's about this IP? IP is nothing but pi by 64. Sorry, IP is nothing but pi by 32 into b raised to 4. From this relation you can get the IP. So already the length is given, already G is given. You can get the value for this one KT. Okay. So here if we substitute the value for KT, substitute the value for I, what do you get? You can easily get the value for CC. Okay. So once you get the value for the CC, see this relation already available with us. From this relation, what do we get? You can easily get the value for C. Okay. Now next one, my next target is to get the value for what would be the frequency if the disk is removed from fluid. Okay. You have to find out the value for the frequency. For that, we know this relation T equals to this one 2 pi divided by omega d, means you need to do calculations for this one damped natural frequency. Okay. So what's about the value for omega n? Square root of kt by k by m means here k by I. In this way you have to just write a relation here. Okay. So from this relation get the value for which one? Omega n. Okay. Further get the value for timing. Okay. So in this you can get the timing and reciprocal of this timing. Ultimately you can get the value for frequency. Okay. Now see the step by step once again. Now the calculations for delta over, my aim is to determine the value for C. For that, already you have seen actually before this steps. Now say get the value for zeta first of all. Okay. From the value of delta, I'll just erase this some portion. Okay. Erase up to here so that I can write easily. So what's about the value for, what's about the relation for zeta? Zeta is nothing but here delta divided by square root of 4 pi square into delta square. Okay. So delta, already calculation for the delta with us for 0.405 divided by square root of 4 pi square into 4.405 bracket square, sorry, term square. Okay. So from this relation you can get the value for zeta as 0.0645. Okay. Now we know zeta is nothing but C divided by Cc. It is the ratio of actual damping coefficient to the critical damping coefficient. Okay. So what's about this C? Therefore C is nothing but zeta into Cc. Now say this Cc, but Cc is nothing but 2 into square root of kt into I. Okay. So what's about therefore can get the value for this Cc like this one. Sorry, C like this one. Cc will come here. So Cc multiplied by this zeta. Cc already with us. Just substitute here. 2 into square root of kt into I multiplied by this zeta term. Okay. 2 into zeta into square root of kt into I. So the information regarding this one diameter and the length of this one brass shaft is given. So in this case, what's about the value for kt? Kt is nothing but here kt equals to GIP or GIP divided by L. So what's about the G? G, modulus of rigidity, already given in the problem. Modulus of rigidity, please erase from here. The modulus of rigidity is given 4.4 into 10 raised to 10. Okay, this is the information given. Length is given 40 centimeter. Okay, after conversion it into meter we can get 0.4. Okay, So this is about the G and this is about the L. What's about the IP? IP is nothing but 5 by 32 into d raised to 4. Okay, like this. So from this one, if I substitute the value for diameter, so diameter is also given here 10 centimeter. Okay, so 10 centimeter. After converting it into meter, you can write this step like this one. So KT, the value for KT after calculation we found 1.08 into 10 raised to 6 Newton meter per radian. Okay. So once you get the value for KT, now if we focus on this step, okay. So what's about the C? C equals to C equals to 2 multiplied by zeta. Calculations for the zeta already done by us here. Okay, point not 645. Okay, this is about zeta multiplied by square root of kt. Kt 1.08 into 10 raised to 6 multiplied by I term. Okay, so this is about the mass moment of inertia. Okay, so here the moment of inertia of the same is given 600 kilogram centimeter square. Okay, if you convert this into kilogram meter square, okay, then this term we found as point not 6. Okay, so you have to multiply by this term by 10 raised to minus 4. Okay, ultimately you can get as point not 6. Okay, so after simplification what do we get? C equals to 32.8 Newton meter per radian. Okay, so this is the damping torque at unit velocity. Okay, then our next target is to find out the periodic time and the frequency, corresponding frequency. Now third point, so third point is nothing but the periodic time of vibration. Okay, that is t equals to 2 pi divided by omega d. We know the relation between omega d and omega n into square root of 1 minus zeta square, like this one. Since omega n is nothing but square root of k by m is the regular formula for the torsional system, kt by this one I. So kt already calculations for the kt with us 1.08 into 10 raised to 6 divided by moment of inertia, okay, already given in the problem 600 kg centimeter square. Okay, after conversion into kilogram meter square we found 0.06. Okay, so after calculations we get the value for omega n equals to 42 4240 radian per second, like this one. So we know the relation between time and frequency. Time is nothing but the here 2 pi divided by omega omega here d. Already we have seen this relation here. So 2 pi omega n with us 4240 root of 1 minus this indicate the omega n multiply by 1 minus is 1 zeta square, zeta with us 0.0645 square of this. So after simplification we get the value for t equals to 0.00149 second. Okay, so if you want to get the frequency in terms of hertz, then 1 upon 2 pi and this one root of 80 pi, this one pi, this relation with us already, this one, this value with us. Okay, nothing but frequency in terms of radian per second, already that value with us divided by 2 pi. So we can get 675 hertz. Or simply take the reciprocal of this one, we found the same answer, that is 675 hertz.